Hi, welcome to this series. There are two different lectures, right, but part of the same topic, which is on Parkinson. Now, we have discussed about epilepsy. We have seen several videos which included craniotomy, then removal of the cortical layer, implanting the device, right, and we talked about surface versus deep implantation. Whether we talk about microneedle or we talk about flexible device, whether it was 32 channel or 10 channel, whether it was non bioresorbable or bioresorbable, but both biocompatible. Bioresorbable when it resorbs in the body, biocompatible when it compatible with the body environment, right? Compatible in vivo studies. So, what we are looking at is the biocompatibility things in the implantable devices, because the device should not harm the other organs when you implant it in the brain. So, in the last video, if you recall, right, what we have seen is that in video number 4, if you recall, right, we have seen that there was a cranial drill instead of complete craniotomy, because we wanted to just place the wires, electrode wires into the brain. So, we do not require a complete craniotomy. Then we saw that the wire electrodes can be used for recording the electrical signals. Again, if the tip of the wire is conducting, then we can just connect and touch the neuron, and if you do that, then you can record the action potentials. But if you look at the group of neurons and you are measuring something from the entire column, which is a cortical column, then you can talk about the LFPs, which is local field potentials. We have also seen how we can drill the ground and reference electrodes using the screw electrodes, and that is important because when you are acquiring the signal or applying the electrical stimulation, there should be a reference and there should be a grounding. We then saw that how we can seal the holes on the skull to fix it, and finally, we have seen how the micromanipulator attached to a stereotaxic apparatus can be used for implantation, because it should be very precise, right. If you are not in the correct position, right, then the whole purpose is defeated. So, you require a micron precision to go deeper inside the brain in the area of our interest. So, that is a use of your micro manipulator, right. Now, what we are going to do in this particular two sets is we look at how we can first understand what is Parkinson, a little bit about Parkinson, and then see that how the gait is affected. I have a video to show it to you. That when a person walks and when the person is turning, then the difficulty of the turning happens because the gait is affected in Parkinson. You have seen Parkinson is nothing but this the vibration or the loss of the motor skills, right, in a certain way. So, for people who have Parkinson, their hands are either shaking, or when they turn around is difficult, or when they hold the pen and they write it's lot of shake, when they eat something with spoon it is shaking. So, this is the motor which is affected. Now, why it is affected, how it is affected is a biology, but can we treat it, what is the current technology to treat it, and what alternatives we can present using the microfabrication that we have learned at the part of this course, right. That is our focus. So, we will not only look at the deep brain, because in Parkinson the way to treat Parkinson is by inserting the electrodes deeper in the brain and applying electrical stimulation and looking at the effect of electrical stimulation. But how about if we have the electrical stimulation at the surface of the brain? We do not have to go deeper into the brain. Now, there is a reason why people go deep, right, but we want to just study how the effect of surface versus deep would be there when you are treating a person suffering from Parkinson. So, for that we have a neurosurgeon working with us who helps us with the surgery. His name is Dr. Sabri Girishan. I am sorry about that, Dr. Sabri Girishan. He is an associate professor in Ramaya Medical College, and he is a neurosurgeon. His interests are in the motor area, and an excellent person to work with, because he actually performs surgery and we learn from him. What we are delivering, what we are designing is electrodes that can be used for such study. So, if you see the slide, right, this is a video that I am playing, and you can see the person walking, right, and then when a person is turning around, you see this lot of difficulty to turn around, right. As soon as the person turns around, the gait becomes normal. See now walking, see it is easy. So, so this is an example of freezing of gait of a Parkinson disease patient. Now, how to treat it is by it is an illustrative diagram, right, of deep brain stimulation in humans, and in terms of numbers 10 million people are affected by Parkinson disease. In short form we call it as PD. This is the numbers are global, which is characterized by tremors, right. I have told you about shaking of the hands. Hand shaking is different, okay, and the tremors are different. So, the instability, posture instability and rigidity. The generally again like any other disease, the Parkinson is also treated by a drug. Some drugs, one of the drug is Parkin, and depending on the amount of Parkinson, the drug is advised to a patient. Most of the patient under drugs, they can sustain, but for the patients who have advanced Parkinson disease, for them a clinical therapy called deep brain stimulation, which includes the surgery and implanting the electrode deeper inside the brain, is advised. Now, in this case the electrodes will apply the electrical signal to regions in the brain such as subthalamic nucleus, also called STN, or pudendoclopontine nucleus, PPN, very difficult name, in which symptoms have been improved in PD patients. So, this PPN has a better than SSN, but STN, but still these studies are undergoing. Several psychological complications and other side effects are observed when you use the STN region, and outcomes of PPN DBS is heterogeneous. So, we want to see, can we use an alternative region along with the surface stimulation, and will it be better for treating Parkinson. Now, to do that, first we need to show it in an animal model. So, here you can see the animal model, the figure which is shown here, right. It shows a schematic representation of the rat during behavioral analysis. What is behavioral analysis? That suppose I put a rat feed container, I put cheese here, alright, and then if the rat is walking on this one, okay, rat walks on this. So, this walking is because there is a treadmill, like you have seen treadmill that we use for walking, right, jogging. Same thing, a rat treadmill is what we can design. It is commercially available as well, and the rat will walk towards this cheese, right. There is a behavior analysis. But if you create a Parkinson in the rat's brain, then the gait will get affected, and if you do the surgery and apply the DBS similar to this humans in the rat brain, right, then whenever there is a gait which is affected due to Parkinson, when you apply electrical signal, the rat should be able to walk in a normal way. So, the gait that is affected, right, can be recovered, and the gating becomes better when you apply electrical signal in the certain area of our interest. Now, like I said, we are not only interested in the deeper area, but also the surface of the brain. Can you use both deep plus surface to see whether it has a combined effect, has a better outcome. So, for this you need to have a wide angle camera, because you need to study the gait of the rat. There is a backpack which applies the electrical signal to the rat's brain. We have the surface electrodes that can be placed on the rat's brain. We have deep brain stimulation electrodes that can go deeper inside the rat's brain, right. So, let us see how we can do that, and in fact we have, at the end of this entire lecture, I will be talking about acute and chronic studies. Like I said that this is a video which will show you what is the difference between acute studies. That means that once you have performed the studies you can euthanize the rat, and when it is chronic studies, that means the rat is kept alive for certain number of days to study the effect of electronics or drugs or whatever it is. Then we will also show you how when we keep the rat in the cage, how the rat is recovered and how the signals can be measured at 3rd day, 7th day and so on. Which signals? Brain signals. So, which are the signals? ECoG. What is ECoG? Electrocardiography. Particularly studying this, we can understand the behavioral analysis of the rat. In the video we will also see the step and behaviors related to the recovery, that is that how the free movement of a rat in the cage will affect the signals. When it is sniffing and searching for the food, then what happens, how it looks like. When it drinks water, how it looks like. When the rat is taking rest, then what kind of signals we can observe, right. We have seen alpha, beta, gamma, theta, right, all these things. So, each signals has a certain characteristics, right, because if it is a sleep mode or it is a active mode or it is an attention mode, then the signals would change correspondingly. Finally, what we will be looking in the video would be the gathering the accustomed to the implant, like how we are getting the signals from the implant, the background of recorded signals and how it can be improvised after it is accustomized. That means that once you acquire the signals, how you can remove the noise from the signals, how you can improve the SNR, whether the signals are the baselines, when there is a Parkinson what kind of changes happens, when you apply electrical signal what kind of changes happen. So, this is the final study, but we will see some part of it as a part of the video at the end of this 2 lectures. Okay. So, to study this Parkinson, now if you go to the objectives of this study, you see the first objective is on design, fabrication and characterization of the rat during behavioral analysis, right. This is the first study, but for that we need to first fabricate the treadmill, and then we can also need to we also need to fabricate the flexible surface neural implant, which is SNI, surface neural implant. Okay. So, as we call it as SNI, and that is using the microfabrication technology, and it will be nothing but a micro engineered electrode array, and that can be used for not only recording the signals, but now we are talking about the applying the electrical stimulation to the certain part of the brain. The second one would be to design, fabricate and characterization of flexible DBS. DBS stands for deep brain stimulation, you can see here deep brain stimulation, right, implant, which we call DNI, surface we call SNI, deep brain we call DNI, again with micro engineered electrodes for deep brain stimulation recording in rat's PD model. PD is Parkinson disease model. The next one would, our objective should be to design and develop a wireless signal conditioning electronics, because if there is a wired, right, again it is a difficulty. So, how about we have a wireless electronics that can, there is a signal conditioning unit for electrical stimulation and recording. The next objective, which is number 4, is to design and develop a catwalk system, right. We call it treadmill catwalk system, which is this entire system we can design, right. Once you understand how the motor works, how to control the motor, right, how to put the belt, how can control the speed, right, how can capture the images, right, you can easily design such a system. This catwalk system can be used for analyzing the gait of the rat during the for the rat PD model, where the rat is in given a Parkinson disease, and when you apply the electrical stimulation. So, you can use this catwalk system to study. The last point, which is to using surface and brain stimulation electrodes to identify novel treating the Parkinson's disease in rat PD models, right. So, we need to find a novel target regions particularly which has surface and deep brain stimulation, how it can help to identify the new or novel target regions. So, this is the problem, right, of Parkinson. I told you that currently the electrical stimulation for advanced PD patients, it is is given in the area which is STN. The alternate area which is studies is PPN, and we are trying to look at not only STN, PPN, but also the effect of the surface electrical stimulation. Now, if you have seen that in one of the video I was talking about this particular region, right, deep brain stimulation region, this region where it is almost 7.8 millimeter deeper in the brain. Now, we are talking about the image of the deep brain located approximately 7.8 millimeter from the surface for the treating the Parkinson. Okay. And here the representative image on the left side is for the brain region for electrical stimulation and recording. Here you can see it is about 3 millimeter, this is about 8 millimeter, same thing here 3 millimeter, this is 8 millimeter, right. So, this is 8, this is 3, this is 3, and that is why our electrode should be designed such that the deeper one we do not worry about it, we can go deep inside in this region, right. But the surface one should be such that it should not be exceeding this region, right. So, can we have electrodes that can come here and can go sit here and can take it. So, we can put electrodes like this, alright. So, we need to design such electrodes using microfabrication technology. Now, the question is that are commercially available surface grids for rodent brain will work for these applications. Now, there is no definitive answer, because again these electrodes are used for certain other applications, but not really for Parkinsonian in the case how we are targeting, okay, the regions that we are targeting. The one that you can see from Cambridge Neurotech, the A1 which is this electrode, alright, this is the zoom in version of the same one, like this one is a zoom in version, is the image of surface ECoG grids connected to a connector. This is surface one, right, connected to this one, while the B, which is this one, shows the schematic layout designs, and C, which is here, right, shows ECoG electrodes from Cambridge Neurotech. So you can very clearly see that the one which you can see, we also have the NeuroNexus products, electrode arrays, and this one particularly, this one is from Cambridge Neurotech, and all these are surface recording electrodes or electrical stimulation electrodes or for ECoG. There are other commercially available device, as you can see in this particular schematic. The company that sells it is called NeuroNexus, and also there is a Thomas recording track neural electrode array. There is also NeuroPixels probe from OpenAccess, and same thing we can also show this particular E1, right, is from Alan. This is developed, signal acquisition system is developed, which is neuropixel probes are distributed by IMEC, right. This one is from IMEC, and the research center developed them, collaboration scientists with Allen Institute, UCL and HHMI in Genelia. So, let us go one by one, okay. Let us not get overwhelmed with the slide. So, if you see this particular needle, right, it looks like a needle, and this needle has a tetrode. You can see 1, 2, 3 and 4, right. So, these are called tetrode. Now, how many tetrodes are there? 1, 2, 3 and 4. So, 4 tetrode across the needle, right, or on the surface of the needle. That means when you apply, and how big it is about 400 micrometer, which is close to 4 millimeter, right. This is 3 millimeter, and you can see here in this case there are linear electrode array. Now, we have seen this thing earlier when I was showing about the linear electrodes, right. So, these are also linear electrodes. The difficulty here is that look at the cost, okay. So, we have not read it. You see A, this one cost $5,000. Let us see in Indian rupees, considering that $1 is 80 rupees, which is not the correct figure, it is 82, but it is okay. We are paying INR 4 lakh. 4 lakh, huge number, right? For one platinum gold iridium connector and electronics module from electrode array and with angular electrode arrangement. But the point is, if you go for B, which is a single needle with linear electrodes, right, this one, it costs about $700. How much? 56,000 rupees, right, crazy, no? So, this is from Neuron Nexus, very costly. You see, my point is these are really good electrodes. Okay, I am not, we should not just learn something from the entire course is, if the technology is there, we should appreciate the technology, right. None of my lecture is against the technology, it is in favor of technology, right. My whole focus is that the technology should be available to people who wants to use it at an affordable rate. The company is there, company should make profit, because that is what companies are for. You take any startup, right. In fact, we are having so many startup because of beautiful policies that are coming up, and that is a good thing, right. Number of startups, number of ideas, number of products, and number of business growing, people are hiring, and then the startup makes money, the whole business grows. Every company that is there has to have some profit, that is called business, otherwise what is a business, right. But the point is 4 lakh value or 56,000 affordable to scientist who knows how to use this electrode in the rat's brain, can use those. When you are learning neuroscience, when you are learning how to do the experimental neurophysiology, when you want to implant those electrodes, would you be given as a student a electrode of 4 lakh and say go and do it? That is difficult, right. So, what I am suggesting right now is not something which is available here. This is a beautiful technology that is developed by the companies, where is Neuron Nexus, where you talk about the IMEC, right, you talk about the HHMI, Gelinia, UCL, Allen Institute. The collaboration is how the things comes up. My point is, can we fabricate this kind of electrodes at 1/10 of the cost or even lesser, so that the researchers can use it, right, and they can fabricate it. Why the cost is so high? There should be some reason. One is, of course, there is a business. What are other reasons that we need to learn? Is the electronics very high? Is the fabrication cost very high? If the fabrication cost is very high, can we fabricate at a lower cost? Can we fabricate indigenously here? What do you require? You require a fab lab. Do we have fab lab? Yes, we have a fab lab. Can you try to fabricate it? Yes, we can, and we were able to fabricate it, right. You require an optimization strategy to fabricate those electrodes that is affordable, that can be used for such application, whether it is epilepsy, whether it is Parkinson, and so on and so forth, right. So, it is about the affordability, so that many people can explore. When many people works to focus on the area of neural engineering, there will be lot of solutions that would be available, right, for surgeons to take up, and the technology that can be developed from not only fewer countries, but from several countries, right. So, that is the whole idea of telling you about this probe. Is not just cost, is about the is not about the technology as well. The technology is excellent, we can use it, right, but can we fabricate it right here? You see this one, this beautiful electrodes, and there is a reason of having different length, right, because what is an application, right, where you are actually placing those electrodes. If you talk about hippocampus, then the whole design would be different. So, these are some commercial devices that we understood, right. The C, which is the one that I have just talked about, right, is thermos recording, is called TREC neural electrode array with an angular electrode arrangement. The image shows a 5 tetrode array with 20 recording channels. This is with 20 recording channels, okay. And finally the D, which is here, shows the neuropixel probe from open access and so on and so forth. So, let us go to the next slide. The downside, right, again we need to appreciate technology, we also have to see the gaps in the technology. So, the downside to the commercially available implants, right, are: 1, surface neural implant, larger grid area, complex surgical procedures and high chance of infection, right, because of the larger grid area. What is the second point? Current requirement, electrode materials like platinum, gold, etc. has shown and has already low safe charge injection limit, okay. And if you want to improve it, then the literature shows that if you go for conductive polymers like PEDOT-PSS, it may help in improving the charge injection limit, particularly important when we are looking at the current requirement, particularly important when we are looking at the electrical stimulation. The next one is that deep neural implant. So, surface neural implant and deep neural implant. So, deep neural implant, you have mechanical flexibility and shape. One mechanical flexibility, that red tissue has elastic modular range of 0.1 to 1.2 megapascal approximately. So, the silicon based implants have very high elastic modulus, about 60 to 300 gigapascal, while the polymer substrate has advantage compared to the harder implants, right. That is why can we go for a softer material like polyamide instead of using silicon based implants. People have tried, and it has shown a better efficacy compared to the harder implants. Finally, talk about the shape. The shape, sharp edges, right. See the sharp edges, you can see that all these edges are very sharp, right. Take anything very sharp, because like a needle. So, the sharp edges causes more trauma or has more trauma during and after insertion. Then second one is cylindrical shape implants induce less trauma. So, can we change the shape from sharp to cylindrical, right, that will help in reducing the trauma. Now, for this, right, we have seen what is Parkinson, we have seen what are the commercial electrodes and what are the objectives, the red based PD model that we are trying to use for understanding the effect of electrical signals, and finally what are the commercial implants and its downside. Now, in the next lecture we will continue with the fabrication of the devices that are used for surface electrode recording, and followed by the materials that can be used for the deep brain stimulation. So, till then, if you have any questions, feel free to ask me. I will see you in the next lecture. I have deliberately shortened down this lecture so that it does not become overwhelming, right. Like I always want to stress on this particular point, that if you look at the lecture, whether it is 1 hour lecture or so, whether this is the course or any course that you take, right, you just focus for half an hour, take a break for 10 minutes, again come back and focus for half an hour, right. Max you stretch for 45 minutes to 1 hour, that is it. After 1 hour you take a break, come back. There is a reason, because the focus and the attention, right, it reduces with time. So, it is shown that after 45 minutes or 1 hour of the work, if you take a 5 minutes break, just walk, come back, right, you can again be attentive. So, that is the reason that you can always come back and see or continue with the lectures. So, I will see you in the next class. Till then you take care, bye.